Studies Section 5, Fraction Approximation, Introduction. Up to this point, we have not considered a situation whereby the second derivative turns out to have zero value at the stationary point. If this is the case, none of the methods discussed earlier could handle the situation. This chapter will discuss how such problem can be handled. To be able to handle this task appropriately, we need to intimate ourselves with expansion of a function around point x is equal to 0 or around any point x is equal to x0, where x0 is a specific value not equal to 0. The former is called Maclaurin series, while the latter is called Taylor series. To expand a function y equal to function of x around 0, x is equal to 0 in bracket, means to transform that function into a polynomial form, in which the coefficients of the variable terms are expressed in terms of the derivative values function of x, f prime of x, f prime prime of x, f prime 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 of x, etc., all evaluated at the point of expansion 0. For the Taylor series, the evaluation is done at the point of expansion x0, that is, f prime into bracket x0, f prime prime into bracket x0, f prime 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 into bracket x0, etc. The result of expansion is a power series because, being a polynomial, it consists of a sum of power fractions. Function approximation of Maclaurin series. Consider the polynomial function of the nth degree. F of x is equal to a0 plus a1x plus a2x squared plus a3x cubed plus a4x raised to power 4 plus dot dot an x raised to power n, equation 5.1. The power series after expansion will involve the derivation of various orders of the function f. Thus, by successive differentiation of equation 5.1, we have the equations as follows. We discover that successive differentiation reduces the number of terms by 1 until in the nth derivative, we have a single product term which is constant. These derivatives can be evaluated around any value, but the case we are considering is its evaluation around x is equal to 0. For x is equal to 0, all the constant terms in equations 5.2 through 5.6 will drop out, and what will be left is the equations below. Let us adopt a shorthand to reduce this long term, assuming that n factorial, pronounce it as n factorial, is equivalent to n into bracket n minus 1, n minus 2, n minus 3, equation 3, 2, 1, such that 2 factorial will be 2 times 1, and 4 factorial will be 4 times 3 times 2 times 1 is equal to 24. A special case is where 0 factorial is equal to 1. Note that we can write equations 5.7 to 5.10 as written below. If we substitute equations 5.11 through 5.15 into 5.1, we have f of x is equal to f of 0 plus f prime of 0 x over 1 factorial plus f prime prime of 0 x squared over 2 factorial plus f prime 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 of 0 x cubed over 3 factorial plus f raised to power 4 of 0 x raised to power 4 over 4 factorial plus f raised to power n of 0 x raised to power n over n factorial, equation 5.16. This new polynomial function f of x, which represents the expansion of the function f of x around 0, x is equal to 0 in bracket, is called Maclaurin series of the polynomial function. The important thing to note is that the point of expansion 0 is the value of x that will be used to evaluate f of x and all its derivatives. Examples: 1. Find the Maclaurin series for the function y equal to f of x is equal to 2 plus 4x plus 3x squared. First, take the derivatives. F prime of x is equal to 4 plus 6x, hence f prime of 0 is equal to 4. F prime prime of x is equal to 6, hence f prime prime of 0 is equal to 6. Thus, the Maclaurin series is f of x is equal to f of 0 plus f prime of 0 x plus f prime prime of 0 x squared over 2 factorial is equal to 2 plus 4x plus 6x squared over 2 factorial is equal to 2 plus 4x plus 3x squared. The last two lines are used to verify that the Maclaurin series correctly represents the function. Prove that the Maclaurin series of the function g function of x is equal to e raised to power x is equal to 2.71828. Generate the derivative of various orders for the function. Note that the derivative of e raised to power x is e raised to power x. Hence, that the derivative of g function of x is simply e raised to power x. The second, third, up to n derivative will be e raised to power x. Hence, we will evaluate all the derivatives at the expansion point x is equal to 0. We have g prime of 0 is equal to g prime prime of 0 is equal to g prime 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 of 0 is equal to g raised to power n of 0 is equal to e raised to power 0 is equal to 1. By setting x naught is equal to 0, the Maclaurin series of e raised to power x is e raised to power x is equal to h function of x is equal to h function of 0 plus h prime function of 0x plus h prime prime function of 0x squared over 2 factorial plus h prime 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 of 0 x cubed over 3 factorial plus h raised to power n of 0 over n factorial. The Maclaurin series may then be expressed as a convergent infinite series as follows: e raised to power x is equal to 1 plus x plus 1 x squared over 2 factorial plus 1 x cubed over 3 factorial plus 1 x raised to power 4 over 4 factorial plus 1 x raised to power 5 over 5 factorial plus dot dot. For x is equal to 1, e is equal to 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial plus dot 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 is equal to 2 plus 0.5 plus 0.1666 plus 0.041666 plus 0.008333 plus dot 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 is equal to 2.718. Function approximation of Taylor series. As said earlier, it is possible to expand an equation at any point x naught, not necessarily 0. Without loss of generality, let us use example 1 as our guide in explaining Taylor series. For pedagogy, let us import the equation down here. Y is equal to function of x is equal to 2 plus 4x plus 3x squared. For expansion around a specific point x naught, let us assume that a given value of x is actually the deviation of x naught. In this case, x is equal to the deviation value, say the x or the and x naught, that is, x is equal to x naught plus the x, equation 5.16. If we substitute the RHS of 5.16 for x in our example, we obtain another function as follows. Y is equal to function of x is equal to 2 plus 4 into bracket x naught plus dx plus 3 into bracket x naught plus dx bracket squared. Equation 5.17. F prime of x is equal to 4 plus 6 into bracket x plus dx. F prime prime of x is equal to 6. Now we know that x naught is a fixed number, a chosen number. Hence, the x is the only variable in the function. It follows that f of x is a function of the x. If we let h function of x is equal to the x, then h dx is equal to 2 plus 4 into bracket x naught plus dx plus 3 into bracket x naught plus dx squared, equivalent to function of x. Its derivative r, h prime function of the x is equal to 4 plus 6 into bracket x naught plus dx is equivalent to f prime of x. H prime prime of dx is equal to 6 is equivalent to f prime prime of x. Our understanding of expansion around 0 indicates that the above expansion yields h dx is equal to f function of x naught over 0 factorial plus f prime function of x naught over 1 factorial into bracket x minus x naught plus f prime prime function of x naught over 2 factorial into bracket x minus x naught squared. Equation 5.18. If the x is equal to 0, then according to equation 5.16, x is equal to x naught. Therefore, on the basis of identity, f function of 0 is equal to f function of x naught. F prime function of 0 is equal to f prime function of x naught. F prime prime function of 0 is equal to f prime prime function of x naught. If we substitute this into equation 5.18, we have h function of the x is equivalent to f function of x is equal to f function of x naught over 0 factorial plus f prime function of s naught over 1 factorial into bracket x minus x naught plus f prime prime function of x naught over 2 factorial into bracket x minus x naught squared. For the function under consideration, f of x naught is equal to 2 plus 4 x naught plus 3 x naught squared. F prime of x is equal to 4 plus 6 x naught. F prime prime of x is equal to 6. Therefore, applying equation 5.18, the Taylor polynomial expansion becomes f function of x is equal to 2 plus 4x naught plus 3x naught squared plus 4 plus 6x naught in bracket x minus x naught in bracket plus 6 into bracket x minus x naught squared over 2 is equal to 2 plus 4x plus 3x squared. The generalization to the nth degree polynomial of equation 5.18 gives the Taylor's formula given in equation 5.19. F of x is given according to the equation. The difference between Maclaurin's series and Taylor's series is the replacement of 0 by x naught at the point of expansion and in the replacement of x by x minus x naught. The interpretation of equation 5.19 is that given nth degree polynomial function of x. If we let x is equal to 5, say, in the terms on the right of equation 5.19, if we select an arbitrary number x naught, then evaluate and add these terms, we will end up with exactly f of 5, the value of f of x at x is equal to 5. Let us assume that x naught is equal to 4. We can write equation in example 1 as follows. Taylor's theorem. This theorem says that given an arbitrary function, u function of x, if we know the value of the function at x is equal to x naught, u function of x naught, and the values of its derivatives at x naught, u prime function of x naught, u prime prime function of x naught, u prime 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 function of x naught, etc. Then this function can be expanded around the point x naught as follows, where Pn represents the terms in the bracket and Rn denotes a remainder. Because equation 5.20 bears Rn, it is called Taylor's formulation with remainder. The form of Pn and the size of Rn depend on the chosen value of n. The larger the n, the more terms there will be in Pn, while Rn will assume different value for each different n. The appearance of Rn is used to capture the polynomial expansion of arbitrary function u, which cannot always be transformed exactly into, but can only be approximated by the polynomial form of Taylor's formula. Thus, Rn supplements for the discrepancy between mean function of x and Pn. If we choose n is equal to 1, we will have the equation below, a linear approximation with n is equal to 2. The equation, a quadratic approximation. Example, expand the function u function of x is equal to 1 over 1 plus x around the point x naught is equal to 4, as written below. Setting x naught is equal to 1 and utilizing the obtained derivative, we get the following Taylor series with remainder. U function of x is equal to 1 over 2 minus 1 over 4 into bracket x minus 1 plus 2 over 8 into bracket x minus 1 squared plus 3 over 16 into bracket x minus 1 raised to power 3 plus 4 over 32 into bracket x minus 1 raised to power 4 plus R4. Using Pascal triangle for polynomial expansion, we have u function of x is equal to 31 over 32 minus 13 over 16x plus 1 over 2x squared minus 3 over 16x cubed plus 1 over 32 x raised to power 4 plus R4. If we know the value of x, then we can get the approximate value of the u function of x expanded at x naught is equal to 1 and n is equal to 4. Exercises. 1. Expand the function u function of x is equal to 1 over 1 plus x squared around the point x naught is equal to 3. 2. Consider the function v function of y is equal to 1 minus y squared in bracket, y plus 4 in bracket. Expand the point around x naught is equal to 4. This is the end of study section 5. Thanks for listening.